And those three things will be what we'll need to get us started in finding solutions. Because if you'll recall from last time, we wanted to solve cosine of theta is equal to a third. And inverse trigonometry gives us one solution. If you want to solve cosine of theta equal to a third, inverse cosine of one third is one such solution. And then you can use, well, the symmetry of cosine. Cosine is an even function. So if you take that solution and reflect it over the y-axis, you get negative inverse cosine of a third. There's a second solution to this equation. Once you have those two solutions, well, there are only two solutions between any interval of length 2 pi. So just add 2 pi's to all of those. That gives you all of the solutions to that equation. Let's do something similar and find all of the solutions to the equation sine of theta is equal to 1 over 3. What's one solution to sine of theta equal to a third?
Inverse sine of 1/3 equals 7.
Yeah. There's one, inverse sine of a third. And let's see, that will be the unique solution to that equation between negative pi over 2 and pi over 2. And let's see. There's negative pi over 2. There's pi over 2. It looks like we just found that solution. How can we find another solution to this equation? Let's even just find it on the graph and then figure out where it should be. So it looks like there's a second solution. And let's just try to figure out where that must be. Maybe even drawing a picture would be a useful thing. So let's draw a unit circle. There's a unit circle. And I want to think about sine of theta. Is sine of theta an x coordinate or a y coordinate on the unit circle? Y. It's a y coordinate. So I'll draw a line at y equals 1/3. It's not a very good circle, but it's a good enough picture to see what we need. There's y equals 1 over 3. And we just found that angle. Because inverse sine, always looking at a quadrant 1 or quadrant 4, so it's that one. How would you describe, how do you go from this solution to that solution? What geometrically do you do?
Flip over the y-axis.
You flip over the y-axis. So to get to here, looks like we need to flip over the y-axis. And what does flipping over the y-axis do to angles?
Inverts the x-coordinate.
Yep, makes the x-coordinate negative. What does it do to the angle now? Not quite negative. Yeah?
Is it pi minus that angle?
Yeah, it's pi minus, because you would go forward by pi and then backwards by that little angle theta. So here's a second solution. A second solution is pi minus sine inverse of 1 over 3. And here it's using the identity that sine of pi minus theta is the same as the sine of theta. And the reason that that identity is true is because of this picture. Cool. So there's this solution. Pi minus sine inverse of 1 over 3. So now that we've found two solutions to this equation, how can we find all the solutions? At 2 pi k's. Once you've found two solutions to a simple trig equation, which both lie in an interval of length 2 pi, then you found all of them. Just say plus 2 pi k enough times. So all of the solutions are given by the two solutions we found, inverse sine of 1/3 plus 2 pi k, and pi minus inverse sine of 1/3 plus 2 pi k. Everyone feel pretty good? And you know what, let's just take a moment and see if we can simplify. Is inverse sine of a thought an angle that you know by looking at a unit circle? No, so it doesn't simplify. If it had been like 1/2, then you know an angle, an actual inclined angle whose sine is 1/2. I guess that would be pi over 6. So we replace all of those inverse sines of 1/1000 with pi over 6 and simplify. But we can't because we don't have an exact formulation of that in terms of something like that. So, on this next page, up here are some helpful flowcharts. So whenever you see an equation of the form cosine of x is equal to a number c, well, here's what you should do. So first you should ask yourself if there are any solutions. All right, so if that c is like 5, how many angles are there with cosine of theta equal to 5? 0. There are none. Cosine is never bigger than 1. So if your number c is bigger than 1, even in absolute value, like there's also no solution to cosine of x is equal to negative 5. Then there are just no solutions. If c is equal to 1 or negative 1, well then a little bit of the work we just did kind of goes sideways. Because the initial solution you would want would be like inverse cosine of 1 is 0. So there's your first solution. The second solution would be negative 0, which is still 0. So there's no point in finding that second one if it's the same as the first. So then all of your solutions are just 0 plus 2 pi k, or just 2 pi k. Something similar goes on at negative 1. So your starting solution is pi. So the next solution would be negative pi. But what's the difference between pi and negative pi? 2 pi. So that would be picked up in the plus 2 pi k anyhow. So all of the solutions are just anything that looks like pi plus 2 pi k. Otherwise, the general case, you'll find your two starting solutions, inverse cosine of c and negative inverse cosine of c, or well, if you happen to really want your angle to live between 0 and 2 pi, that one's actually between 0 and 2 pi. So you wouldn't want to include both of those as initial solutions because they're like the same point on the unit circle. And then you would take those two and add 2 pi k's to get all of the solutions. To work with sine, do something really similar. If c is too big, there are no solutions. If c is equal to 1 or negative 1, well, there's like only one point on the unit circle corresponding to both of those y values. So those would produce all of your answers. I guess I'm missing a negative sign right here. In the general case, there's inverse sine of c and pi minus inverse sine of c. And then those two solutions plus 2 pi k's. And maybe I'll point out that if you see something of the form inverse sine of c, where c is a number you see on the unit circle, you should simplify. So if you see inverse sine of 1/2, that's pi over 6. Inverse sine of root 2 over 2, it's pi over 4. And to work with tangent, it's even easier. And maybe I'll draw a picture of why it's easier. I'll draw a picture of tangent. So let's see, I'll draw this line here at y equals c. I guess here I'm assuming c is positive. No matter where that red line is there at least one solution to that equation? Yeah, that red line definitely crosses the blue curve. And it looks like as soon as you find one solution, then you can shift by pi's to get all of the solutions, because tangent is pi periodic. And so if you want to write down all the solutions, well, get your seed solution, inverse tangent of c, simplify as possible, and then add pi k. Everyone feel pretty okay? So let's use these flowcharts to solve some equations. So here is the content of this document from here. We will solve these two trig equations immediately. It'll take like no time. We'll basically just write down the answer. This one will be more involved. we'll do one for sine. And as soon as you can solve things that look like trig function equals number, then you can solve things that are more complicated that involve trig functions. You can solve things like 3 times the sine of x plus 2 is equal to 1. You can do some algebra and then solve a simple trig equation. And what we'll do from there is we'll just increase complexity by 1 with each step from there. Any questions right now? Nice. So let's solve this. Let's solve tangent of x is equal to -8. So by looking at that flowchart, what is the seed solution we should use? Inverse tangent of -8. All right, and how do we get all of the solutions once we found one of them?
Plus pi.
Yeah, tangent is pi periodic. So once you find one solution, you can find all of the solution by adding pi's. Those of you who like to put a plus or minus instead of a plus to emphasize that that multiple of pi could be negative, do it. Yeah.
And then, yeah, the number won't matter if it's bigger than 1 because our range goes for up or down, correct?
Yep, so there's no subtlety with tangent in terms of is this actually a valid solution. So let's go ahead and do a quick check. Let's figure out if this is actually correct by, well, I guess we could do one or two things. We could look at a graph, or we could literally just plug in some of these numbers to that formula. And people would like to look at a graph. I don't know if people would rather plug in some numbers. Let's plug in some numbers. So, click, 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 click. So this is exactly what I'll do. Let's compute the tangent of the arctangent of -8. And that had better be 8 again. Oh, nope, -8 again. And indeed it is. But that's only one of the possible solutions. What is another of the solutions that our formula suggests? That plus pi? Oh, come on. Oh, I hit the wrong button when I went to copy. I understand. -8. Okay, cool. I think I believe it. So just as Paul always, there's no reason to ever have a wrong answer because you can check if you've actually solved the equation by back substituting. People feel okay? Nice. So let's do it again. Let's solve tangent of x is equal to the square root of 3. Well, let's actually do one quick check on the -8 first. By looking at the unit circle, do you see any angle where the ratio between sine and cosine is exactly -8? Nah. And let's start by drawing just enough of the unit circle. So let's see, this point is at 1, 0. And remember, tangent is the slope. So what's the slope of the line from 0, 0 to 1, 0? 0. So this point has tangent equal to 0. Root 3 over 2, comma 1 over 2. So what is the tangent corresponding to that? Right, it'll be y over x. Be this divided by that. The over 2's will cancel. You'll get 1 over root 3, or simplified root 3 over 3. Here we see root 2 over 2, comma root 2 over 2. So what's the tangent of that angle? 1. And this point is 1 over 2, root 3 over 2. So what's the tangent of that angle? And these will be like the same, but the y coordinates will be negative. So are any of those tangents plus or minus 8? Nope. So there's no simplification to be done. Let's do this next one. Let's solve tangent of x is equal to the square root of 3. So first things first, we need a starting solution. What is the starting solution to use according to this flowchart?
Inverse tangent of 5, 3.
Well, it's inverse tangent of root 3
Yeah, yeah.
plus pi k. But what is the inverse tangent of root 3? Pi over 3, because we see there's an angle where tangent is equal to root 3. People feel pretty okay about that? So it's important to simplify when you can. And let's do one other simple trig equation. Let's solve sine of x is equal to negative a half. So remember, this one is more complicated. We get two starting solutions. So what's the first starting solution we get?
Inverse sine of -1/2.
So the starting solution is inverse sine of negative 1/2. And let's simplify if possible. What's the inverse sine of negative a half? How many people have a unit circle on them? Yeah, so try to consult that or use the fact that you've got a unit circle emblazoned into your brain at this point, I hope. So
All would be negative because we want between them.
So from the point of view of solving the trig equation, 11 pi over 6 is just fine. This procedure doesn't say if you don't start with inverse sine, then you're just wrong. But if we've written down inverse sine of negative 1/2, then it really should be negative pi over 6. If we hadn't already written down inverse sine of negative 1/2, and then you had said 11 pi over 6, then I would have been just fine with it. So there's a starting solution. The second solution is the solution we get by reflecting over the y-axis. So what's the second solution you see?
Pi minus inverse sine of -1/2.
Yeah, so there's the first solution. The second solution is pi minus negative pi over 6. Because it should be pi minus the first solution. Now what does that simplify to? What's minus a negative? A positive? So it'll be pi plus pi over 6? 7 pi over 6. Alternately, is that an angle that's on the unit circle? So when it's a number that you actually see on the unit circle, you can forego all of this inverse trigonometry stuff. Same as if you wanted to solve 2 to the x is equal to 4, you would just say, oh, well, the answer is 2. You wouldn't need to deal with logarithmic stuff because you just know the answer. If the unit circle just has your answers there for you, you don't need to do the inverse trigonometry. So now that we found two solutions, how do we find all of the solutions? Add plus 2 pi k. So all solutions are x equal to negative pi over 6 plus 2 pi k, or x equal to 7 pi over 6 plus 2 pi k. And maybe I'll point this out. If instead of this you had 11 pi over 6 plus 2 pi k, would that also be correct? It would. Right, because you're allowed to add a multiple of 2 pi anyway. And notice those two differ by a multiple of 2 pi. So if you do it following whatever algorithm you follow, someone else follows a different algorithm, but still finds two seed solutions, then you can have the same family of solutions even though your answers will look different. If you want to check that your family of solutions are the same, check your two seed solutions and see if they differ by a multiple of 2 pi. Everyone feel pretty okay right now? Any questions right now? Okay, then let's go ahead and begin. So let's solve complicated trig equations. So trig equations, there's some trigonometry going on, but there's a little bit of algebra. And we'll start with something reasonably light. Let's try to solve this. Let's try to solve 3 times the sine of x plus 2 is equal to 1. And as a first step, let's try to reduce it to a simple trig equation. So I'll go ahead and set s equal to sine of x, so I have to write sine of x less often, and solve the equation 3s plus 2 is equal to 1. So what do you get from s when you solve that? I hear a negative 1/3. Is that agreed? S is equal to negative 1/3. So now we are down to the situation sine of x, because that is s, is negative 1/3. Is that something we can just use the flowchart to solve? I guess so. What is the first solution that you should see to that? X equal to inverse sine of negative 1/3. And then you can add a 2 pi k to get all of the solutions corresponding to that point on the unit circle. What is the second solution?
Pi minus inverse sine of negative 1/3 plus 2 pi k.
Pi minus inverse sine of negative 1/3 plus 2 pi k. So maybe I'll point out one simplification here. Inverse sine, is it even or is it odd? Picture the graph of inverse sine in your head for a second. Even or odd? Let's remember it. Let's draw it together. So I'll start with the graph of y equal to sine of x. But only the chunk that I actually use. So there's the graph of sine of x. But only the piece that actually gets inverted. And now I'll flip that over the line y equals x. Oops, that was a mistake. By looking at that graph, is that function even or odd? Odd. So what can I do with this negative sign inside of that inverse sine? I can pull it out front, where it will cancel with that negative sign. So that simplifies to inverse sine of 1/3 plus pi plus 2 pi k. So you can do some simplification. You can recognize that inverse sine is odd. If that were cosine, could I have done that?
Oh, it's t.
Yeah, it's neither. All right, the graph of inverse cosine looks something like that. Cool. Let's do the same thing. Let's solve. Well, maybe I want you guys to do this. Solve for me 5 times the tangent of x plus 2 is equal to 1. just like the example we just did. Step 1 is figure out what tangent of x has to be. Get the equation you have something that looks like tangent of x is equal to a numball. And then use the flowchart, which says that solving equations that look like tangent of x is equal to a numball. Well, that's easy to do. So what's the solution to this equation?
Inverse tangent of -1/5 plus 5k.
Yeah. Everyone pretty happy? Let's check for one simplification. This won't even be much of a simplification. Is inverse tangent even or odd? It's odd. So I could conceivably take this minus sign and pull it out front, but there's nothing there to cancel it with, so maybe that's not an improvement. You could pull that negative sign out if you wanted to. Anyone want to see that one walked through slowly? Okay, good. Everyone's pretty happy about that. So the plan from here is we'll ratchet up complexity by just a little bit each time. Let's try to solve this equation. 2 times the square of the sine of x minus 5 times the sine of x plus 2 is equal to 0. So the algorithm is the same. Step 1, solve for sine of x, because that's the trig function I see this time. And again, for convenience, I'll say, well, I'll replace the sine of x by s, so I get 2s squared minus 5s plus 2 equals 0. And that looks like a quadratic equation, so I bet you could use the quadratic formula to solve it. On the other hand, I think it factors. But that's hard to see when there's when it's not monic. So once you get even just the values that s might be, once you solve this equation for s, tell me what you get. Sine of x is equal to 2, and sine of x is equal to 1/2. Anyone get things different? Does anyone want me to talk through that? Okay. Yeah.
So for the next step now, are we gonna have 4 different answers now? Because before we only had one solution, we broke it down into 2 possibilities.
Conceivably, there might be 4 different families of solutions. So since this involves trigonometry, as soon as you get one solution, there are infinitely many. But there might even be 4 infinite families of solutions. Because now we have 2 simple trig equations to solve. The first one is sine of x is equal to 2. What's the solution to sine of x is equal to 2?
One would be the inverse sine of 2. And then the other one would be pi minus the inverse sine of 2. No.
Why not?
Oh, it's 2.
It's too big of a one.
2 is too big. 2 is not in the domain of inverse sine. That has no solutions. Though if you think about trig functions in just the right way, you figure out how to make sense of trig functions evaluated at complex numbers. In which case you'll see that, oh, it turns out inverse sine of 2 is a number, it's just complex. we won't do that in this class. What about sine of x is equal to 1/2? What are the solutions to that?
You have to simplify, but you'll have inverse sine 1/2 plus 2 pi k, and then pi minus inverse sine 1/2 plus 2 pi k.
Yeah, so there are the two infinite families of solutions, but they both simplify. So by looking at the unit circle, do you see an angle in quadrant 1 or quadrant 4 for which sine is equal to 1/2? What angle do you see?
Pi over 6.
Pi over 6. So this first one is secretly pi over 6 plus 2 pi k. And what would that make the second one?
Be 5 pi over 6 plus 2 pi k.
5 pi over 6 plus 2 pi k. So how many people, when they saw this equation, just thought to themselves, well, sine of x is equal to 1/2. That sounds familiar. I'm going to not write down any inverse trig functions and just see if I can see two solutions on the unit circle. That's a reasonable thing to do. All right. Same as if you want to solve something that looks like 5 to the x is equal to 25, you could take log base 5 of both sides, or you could just notice that the answer is 2. People feel pretty okay? Any questions so far? So, I think I'm going to blow by that example because it's just the same thing again, in favor of getting to something more novel. Let's think about problem number 6. As a consequence, I might wind up rearranging the schedule for tomorrow. We'll see. Let's try to solve that equation. 4 cosine of x plus 5 is equal to 4 times the square of the sine of x. So you'll notice all of the problems before this had involved a single trig function, and that's it. This involves two trig functions. So if we were to want to rewrite this as an equation where we've forgotten the trigonometry, we would get 4c plus 5 is equal to 4s squared. But that's an equation with two unknowns. We can't possibly solve it to know everything. We could solve for c or something. But do we know some fundamental identity that relates sine squared and cosine squared? Yeah, what is that identity?
Sine squared x plus cosine squared x equals 1.
Yeah, so let's use that. So sine squared x plus cosine squared x, that's always equal to 1. Could I solve that equation for sine squared of x? So sine squared of x is the exact same as 1 minus the square of the cosine of x. Let's use that. So let's replace that sine squared of x with 1 minus cosine squared of x. So what do we get? We get 4 cosine x plus 5 is equal to 4 times 1 minus cosine squared x. And those parentheses are important because you need all of sine squared of x to be multiplied by 4. Nice. So are we now down to just a single trig function in that equation? So let's simplify it maybe just a little bit. So I guess that'll be 4 cosine x plus 5 is equal to 4 minus 4 cosine squared of x. And so let's go ahead and just set cosine x equal to c, so I don't have to write cosine so many times. I see 4c plus 5 equals 4 minus 4c squared. Does that look like an equation that you know how to solve? I hope so. It's a degree 2 polynomial equation. So I guess the algorithm is put everything onto the same side use the quadratic formula. And so I don't want to do the quadratic formula stuff, so I'm just going to let you guys do it. Once you see what goes in, these two blanks will come together. So what is C?
-1/2.
Yeah. Just -1/2? Because it's not.
Yeah, we got square root 0 in there. So,
Yeah, so the discriminant winds up being 0, so you know there's only one solution, and in fact it'll be rational. So you wind up with C equals 1/2 with multiplicity 2. That tells us something about the graph, but we're not asking about the graph. So we wind up with the equation cosine of x is equal to 1/2. And no second equation whatsoever. Let's solve that using the flowchart. And maybe before thinking about inverse trigonometry, at this point you probably have your unit circle in front of you. By looking at your unit circle, what angles do you see which have cosine equal to 1/2?
2/3.
Oh, right, -1/2, right?
Yep.
I accidentally forgot all the negative signs, but you remember them. So I see x equal to 2 pi over 3, you said? And what other solution do you see by looking at the unit circle?
4 pi over 3?
4 pi over 3. Does that give us two solutions that both lie in the same interval of length 2 pi? So that gives us all the solutions. All the solutions are those two plus 2 pi k. Nice. Yeah.
Yeah, so then the second, so like if you didn't do it that way, like if you did it another way with the flowchart, and we wrote it out like inverse cosine of -1/2, which will get us our 2 pi over 3, but then our second one would be negative inverse cosine of -1/2, correct?
Mm-hmm.
Okay. And then those would simplify.
Yeah, so this would become 2 pi over 3 plus 2 pi k.
Yep.
Or negative 2 pi over 3 plus 2 pi k.
Okay.
And notice, looking at these two different families of solutions, what's the difference between those two things I circled in red? Yeah, it's 2 pi, I think. All right, take the difference between those, you get 4 minus 2 is 6 times pi over 3. Yeah, that's 2 pi.
So that's supposed to be 3 or 4 pi over, or 4 pi over 3. The other over.
Oh, interesting. Yeah, that should be a 3. Cool. And so let's see, maybe I'll point out, so sometimes you, in particular, only want the solutions that are between, say, 0 and 2 pi, or only the solutions between minus pi and pi. When that's the case, you probably want a solution that doesn't involve a 2 pi k. If you want all the solutions between 0 and 2 pi, there are the two solutions that lie between 0 and 2 pi. If you want all the solutions that lie between negative pi and positive pi, there's one, there's the other. Cool. And let's see, I think we have enough time to make progress on one more. So let's try to solve this is the last thing that we'll do today. Let's find all the solutions to 3 times the tangent of 2x minus 1 plus 2 is equal to 1. So step 1, I'll solve that for tangent of blah, blah, blah. So I'll pretend there is no trig function there. I'll just write 3t plus 2 equals 1. So what do you get for t? I guess you get negative a third.
Yep.
So that means that t, which is the tangent of 2x plus 1, is negative 1 over 3. So now I'll treat 2x plus 1 as a variable. I don't know, maybe I'll call this u for now. So if you want to solve tangent of u equal to negative 1 over 3, you know how to, right? What's the seed solution to that equation? Tangent inverse of negative 1 over 3. Then I guess there should be a plus pi k. But is u the thing that I wanted to find at the beginning? Well, not quite. I wanted to know what x was. So I need to solve 2x plus 1. Well, that's the same as the thing that we just called u. And we just found that u is equal to tangent inverse of negative 1 over 3 plus pi k. Well, but that's easy, right? That's a linear equation in x now. So it looks like I can just add 1 to both sides and then divide by 2. So I'll get 2x equals tangent inverse of negative 1 over 3 plus 1 plus pi k. So x is equal to all that divided by 2. Tangent inverse, negative 1 over 3, plus 1 plus pi k. Oh, parentheses should match up. Divided by 2. Michael, okay? Nice. So I'm about at time. I didn't finish all the examples I wanted to today. So stay posted to the webpage. I'll decide whether I want to do more examples like this before having that group activity. I'll meditate on that for the next 23 hours. Or some subset there. As people are about to leave, Josiah's evil. Haojun Cheng. Philippe Laporte. Mai. Erica Yan. Very good. And let's see, if you either didn't get your midterm back or you got the midterm back, but it looks like I didn't actually look at your review and you turned the review in, we should have a conversation. Good. Or if I just failed to actually add up numbers on your exam correctly, that's also something I'm pointing out.
Yeah, that's nice.
No, I didn't get it. I knew what I was doing. You?
S1. You in section 1. Yeah, that was just for me to keep track of the sections.
I just came and instead I was like, the last
There's an issue just with the math, they forgot to have the fall semester for 2023.
Yes.
Or for 2022. It's just 2022. Yeah, they forgot that.
So I'm really happy there.
Okay.
And I'm happy there.
Okay.
So let's just talk about how to rationalize the denominator. So you want to do something, because this is bn, it's just not completely simple. So you want to do something that doesn't actually change the value of that number, but simplifies the way it works. And one thing you're allowed to do to fractions is if you multiply and divide by the same number, it's still the same.
Okay. So you multiply by this, like that. pretty sure I did that in my head, but then I looked at all the answers. And I was like,
That's because it still simplifies quantum. You
so
see
like we
anything?
need to do.
Ah, yes, 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 yes. That's perfect.
Get an actual copy of it too.
No, this will do for my purposes.
I only got your email this morning, so I can get a copy tomorrow.
Oh, okay. I understand. You don't have a copy of that. Yeah, yeah, yeah.
Oh, so I got your email this morning. That would work. I have an academic community, like planning meeting tomorrow morning.
Okay.
Like Wednesday morning. So I can like email you back.
Okay. After 30 p.m. also works.
Okay.
So I can make any time between like any starting time between like 7:30 and 3. I can make walk. Because if you show up at like 7:30, I'll just set you up myself.
Alright, I think that'll probably work best. Maybe like Wednesday morning. Get your quiz done now. Things like that.
Yeah. Yeah, we can do that. Send me an email so that I remember to set it
Yeah.
up.
Alright, thank you so much.
Yeah, thank you. I'm glad you're feeling a little better.
At this point, it's more just like stress.
Yeah, and if you need to like step out of the class, I'll understand. Oh, do you have, there was the review for the midterm too.
Oh, I'm like halfway done with it.
Okay.
It'll be done by the time.
That'll do. So, with 5 minutes before start time, people have anything they'd like to ask about? Yeah.
Okay, number 29 on 6.1.
What did it ask?
It says use a calculator to find the value of each expression,
Uh-huh.
rounded into decimal places.
Uh-huh.
Like, so I figured I knew how to do the 27, but then 29 I did it the same way, but the answer in the back of the book was different, and so I couldn't figure out like what I did wrong.
And what did 27 ask you to compute?
The same thing. It was just a different number.
Yeah, but I don't know what the number is.
Oh,
I-
0.1. Or
What?
cosine, inverse cosine of point, or inverse sine of 0.1, sorry.
Ah, excellent. Sine and loss of point.
Yeah, I got that, I knew how to do that one though.
Oh,
But I
okay.
didn't, so I couldn't figure out how to do the cosine of inverse cosine of 0.6.
Okay. So,
So you just do like second cosine 0.6.
I don't know the layout of the calculator, but probably if you hit second and cosine, you get cosine inverse probably.
Yeah.
And then when you evaluate at 0.6.
It was just weird because like that's what I did, but then the answer in the back of the book was different. So I was wondering if maybe that was wrong.
Are you in degree or radian mode?
I was in radian.
Okay, then that should give you the same answer. As that should give you the right answer. But I mean, let's go ahead and do it. Arc cosine of 0.6. You got an answer that was, oh, you can't see that. You got an answer that was about that?
That's what I got, yeah. So then the book is wrong, I think.
I suspect it may be.
Put 1.37.
It said 1.27.
37.
Yeah, before you jump to too strong a conclusion, make sure that that is actually
Okay.
0.6.
Okay.
Yeah, so as usual,
I'll go double check everything, but
the reason I assigned the compute these using a machine problems is just to push home that you should be able to use a machine to do these computations. But since really what I'm testing is, can you get your calculator to work? Like, I don't think I've ever had the grade or grade 1 of those in the past. But yeah, think on it. Which number was that? That was 20.
29. Oh, okay.
Oh, you did the wrong one.
Yeah.
Ah, okay.
That was the problem.
That solves that.
Okay.
Very good. Cool. Any other questions people want to ask about? So, let me begin handing these back. Paul Bishop. Ellington. Lauren Casey. Henry Serdarian. Sophia Chaconis. Jeannie Purchase.
Yeah, I went with
Dollar. Josephine Demar. Sarah Deschler.
I got 6, so I'm not here.
Rob Foy.
I was like, oh, thank goodness, how's the work this week? And then I got out. Yeah. No. I was over Canada. Oh, you were? Yeah, but I didn't.
Okay, give me that back. Because I think that's your minimal.
2 hours.
Justin Grace.
So I went down and I was
Randy Granquist. Kyle Figure.
yeah.
Sierra Heaton. Jackson Hughes. Morgan Henson. Nick Vaughn.
Not even. Yeah. He's got 9 editor. And now November. He's getting evicted. He's getting evicted from
Christian Matson. Morgan McErvin.
Well, it's not getting in trouble for the same thing over and over again.
Olivia McFarland.
So it depends on how he's getting it evicted. Yeah.
Jamar McWatry.
Everybody.
No, just give me the pass that down.
So, yeah, she does.
Taylor Montgomery.
I don't know.
Caitlin Patrick.
Oh, there?
Lauren Evans. Brett Phillips.
That is so much money. Yeah. Oh, like that. Well, you should make it.
Nate Tweets. Nick Watt.
No, that was just the money.
What here?
Yeah. They said they doubled their commissions. Yeah.
Dave Heaney. Noel Olaub. Annabelle Wilsonski. Finally, James Lott. All right, last calls for Cole Bishop, Sophia Chaconis, Josephine Demar, Sarah Deschler. Right there. Sterling Place, Taylor Montgomery, Nathan Waugh, and yeah, there you are. Annabelle Wilsinski and James Lennon. Cool. So, maybe a note about how the scoring is. There might be on the top of your exam as many as 4 different numbers would look like they might be the score on the exam. So here's how the grading went. So first I graded it, each of the multiple choice below me, all and none on the course pass them. That's the smallest of the scores you see. Then I went through and looked at each multiple choice problem. If you did it wrong, but like did everything correct and then like screwed up the simplification, then you got 3 out of those 5 points. And then I added those up, I gave you those points back. That's the one that's labeled as partial credit. If that totaled at or above a 90%, I didn't read anything else you wrote. If then you turned in the review document. For each one you got wrong on the exam, I looked at the review document. If you did the corresponding stuff on the review completely right, you got as many as 3 points back on each point. I then tallied up that instead of the points back for partial credit. So there's a third number you might see. If that score was still below an 80%, then on each problem I gave you the maximum of the points back between partial credit and doing it correctly on the review. But that score was capped at 80%. So that's how to read, that's how the scoring was done. Any questions about that? The question can possibly be you enter my score on Canvas incorrectly or you failed to add these numbers correctly. Okay. If you do have any concerns about your exam, we can have a conversation. So let's go ahead and do what I want to do today. I don't need to still be recording.